this is Jackson Baker, and today we are going to do some calculus. So in the problem, we are given this infinite sum. It says the sum from n equals 1 to infinity of 1 over n times the square root of n squared plus 1. And we already know that this sum converges due to the p-series test, where p is greater than 1. But for this one, we are asked to find the exact sum. So finding exact sums is usually very difficult. There's no real method that's consistent and works for a ton of things. You kind of just have to try it out for yourself and see what works. So we're going to write out the first few terms, see if there's a pattern, anything like that, and we'll go from there. So first term is 1 over, plug in 1 for both of those, and you get 1 over root 2. Second term is 1 over 2 root 5. Third term, 1 over 3 root 10. Fourth term, 1 over 4 root 17. So from what I'm seeing, there's no good pattern, and we're never going to get out of the square root because the n squared plus 1 is never going to be big enough to advance to the next square. So like if you have 6 squared, which is 36, to get to 7 squared, you're going to need a lot more than 1. For 9, you need 13 here. And this number in between just keeps getting bigger. It's going to be plus 15 here, plus 17 here. And it's never going to be 1, so we're never going to get out of that square root, which is unfortunate. So finding the exact sum, I honestly don't know how to do that. But what we're going to do is we're going to get close. We're going to find an upper limit to what it could be. And to do that, we're going to use a perhaps familiar concept to you. It's called the integral test. So if you have a curve that looks like this, which we do, if you take a look at the right Riemann sum, then you'll notice that all these bars are always going to be under the curve. And if you have the area of the whole curve, then that is going to be greater than the sum of all these little bars. But how do we find the area, you ask? Well, with integration. It's not the funnest thing you've ever seen. But for this one, we can't really go from 0 to infinity because the limit as n approaches 0 is infinity because it just keeps going up here. And I think it'll keep going down on this way, so we really don't know. So what I'm going to do is I'm going to take the limit from 1, or the integral from 1 to infinity, and then I'm just going to add this little bar. So we know that the integral of 1 to infinity of 1 over x times square root of x squared plus 1 dx is greater than the sum of n equals 2 to infinity of 1 over n square root n squared plus 1. And we know that because from this little diagram, you can see that it's going to be greater. So if we do want to get close, we can include more, we can take out more of these because that'll fill in these little areas that we're missing. But just for simplicity, I'm just going to do this one. So our upper limit is going to be 1 over square root of 2 plus the limit, or the integral, from 1 to infinity of 1 over x root x squared plus 1 dx. And to do this, we're going to use some trig sub. Also, this is not very proper, so I'm going to make the limit as a approaches infinity of 1 to a, 1 over x root x squared plus 1 dx. We just do that to make sure that infinity isn't just plugged in. We have to have the limit as something approaches infinity, and it's a lot better. So here we are going to have to use trig sub. We're going to say x equals tangent of theta, and dx equals secant squared theta d theta, which means that this is going to reduce to, or simplify, if we plug in that. We don't know the limits of integration. Well, we can know them, but I'm not going to solve for them right now, as we're changing from dx to d theta. So we get secant squared in the top, and then tangent of theta. Square root of tangent squared plus 1 is going to be secant squared d theta. And we know that this simplifies to secant. It's going to take out one of those, and this simplifies to limit a approaches infinity of the integral from something to something of cosecant theta d theta, which is natural log of sine of theta over cosine theta plus 1. I think there's technically an absolute value here, but in this case it's not really going to matter. Okay, and this goes from something to something as it's still in terms of theta. To get out of terms of theta, we're going to draw this triangle here, angle theta, and we know that the tangent of theta is equal to x. So SOHCAHTOA, we have TOA, opposite over adjacent, is x over 1, making this square root of x squared plus 1. Meaning that we can put this back into terms of x, and it approaches infinity, natural log of x over square root x squared plus 1, because sine is x over that, over 1 over square root x squared plus 1 plus 1. This is going to simplify to, we can have this as x root x squared plus 1 over root x squared plus 1, and then that'll enable us to cross that out. So we have x over 1 plus the square root of x squared plus 1, and that is in the natural log. Sorry about that. And now we know the limits of integration, which is 1 to a. Okay, so if we plug everything in, natural log of a over 1 plus square root of a squared plus 1 minus natural log of 1 over 1 plus, it's going to be root 2. So now, how do we find this? Well, we can just look at the highest power of a. So over here, in the denominator, the highest power of a is a to the 2 over 2, which is a. Highest power here is just a to the first as well. And as there are no coefficients, we know, before I go into this, the limit can go inside the natural log as it is a continuous thing. Continuous function, I guess. And we can move the limit inside, which is nice for this. 1 plus square root a squared plus 1. And If this is a, this is a, there's no coefficients, that will simplify to 1 as a approaches infinity. So ln of 1, e to the 0 is 1, meaning that ln of 1 is 0. So it's 0 minus the natural log of 1 over 1 plus root 2. And we still have to add in this part. 1 over root 2 minus natural log of 1 over 1 plus root 2, which is going to equal 1.58848. And there we are. So again, if you want to get closer to this, you can always take out more of these terms. Like if I took out these terms, added them up, and then added the integral from 2 to infinity, that would also work, and it would get you closer as you're deleting some of this space. And if I had to guess, if this works out somewhat nicely, then I would guess that the exact limit approaches something like pi halves, which is 1.57 something. But here we reached an upper limit, which is 1.58848. It's not exact, but it's going to be really close to what the exact sum is. Thanks for watching, and oh, by the way, if you like my way of teaching, check out the theories of Jay Greasy on YouTube, and I just cover a lot of cool math videos. Thanks for watching.